Good morning, students. We'll move on to the next topic, writing a grammar. So in previous class, we discussed what exactly context-free grammar is, what are the different components of context-free grammar, okay, then different levels of errors, okay, and what is the use of that CFG, okay, that regarding that we had a discussion, like how we can convert the regular expression into a context-free grammar, okay, how to retrieve that terminal and non-terminal, the components of the grammar, okay, everything we studied over there, okay. Now we need to go for a comparison like lexical versus syntactic analysis over there, okay. So after all, we are having the context-free grammar, the advanced kind of version, okay, of a programming language, fine. After having this, still we go for the regular expression. Why we need to go for that regular expression? Regarding that, we have an explanation over here, okay. So the first subtopic will be lexical versus syntactic analysis over there. Everything that can be described or defined by a regular expression can also be described by a grammar, okay. Then why use regular expression to define the lexical syntax of a language, okay. So this is what the question. So for that, we have a complete explanation, 4 to 5 different reasons we have, okay. There are several reasons. The first one, separating the lexical and non-lexical part in compilation process provides the convenient, okay, or like easy way to implement the front end of the compiler exactly, okay. So if you are using the regular expression, okay, we can categorize, okay, which are considered as a non-lexical part and which should be considered as a lexical part over there, okay. That is what the one advantage of using regular expression over context-free grammar over there, okay. So accelerates the process of compilation, okay. Error in the source program can be identified easily, okay. So this is what one of the reason, like few kinds of error, okay. I don't say like the complete and the error analysis will be takes place under lexical analysis, okay. It's impossible, okay. Few kinds of error detection can be possible by lexical analyzer using regular expression exactly. Then the lexical rules are quite simple, and to describe them we don't need a notation as powerful as grammars exactly. So in case of grammar, okay, we are using different kinds of notations over there, like we have two categories of notations. For terminal we are using one, and for non-terminal we are using one, okay, for start symbol and all, okay. So there are different a lot of types of notations we are going to use, complicated versions of notations we are going to use in case of a grammar. But if you go for a lexical part, okay, in case of tokens and regular expression, we are not going to use such a kind of complex version of notations over there. That is also one of the advantage. Then later, regular expression provides easy way to understand the notation for tokens than grammar exactly, okay. So regular expression will help us to understand the tokens compared to the grammar exactly. Grammar will be a bit complex version, fine, okay. It will help for the compilation process, that's obvious, okay. But when we compare the regular expression use in the token and the use of grammar in the syntax analyzer, regular expression will be a bit simple exactly, that's it, nothing else, okay. Both are important, you cannot skip the regular expression or the grammar, both are important. Then later, more efficient lexical analyzer can be constructed automatically from the regular expression than grammars exactly, okay. Like whatever the complex kind of like grammar we want, okay, that can be generated by using your regular expression exactly. Yes, obvious, whenever we have a regular expression, from that we can extract the grammar. In previous class we discussed, okay, in case of handling the relational operator, how it can be done, okay, in case of identifiers, in case of keywords, numbers, letter, digits and all, okay, how we can extract the grammar from those particular regular expression. This we already studied over here, fine. So next topic, we'll move on to the eliminating ambiguity. We'll move on to the next topic, eliminating ambiguity. So here you can observe we got 3 different productions. E derives E plus E, E derives E into E, and E derives ID exactly. So this is what the possible string. Okay, now what exactly ambiguity stand for? Okay, using this production for getting this particular string, okay, if you are able to generate 2 different parse for a particular string, then we call it as, yes, there is a presence of ambiguity in this particular grammar exactly. Okay, now we'll see how we can get this ID plus ID into, sorry, ID plus ID plus ID. Okay, so here just observe, so the initial state we are considered as a E, okay. So what are the possible production values we have? E plus E we have, then E into E we have, and ID we are having, right? Okay, so here what version we want? ID plus ID plus ID we are getting, okay. So now E, if I elaborate it as E plus E exactly, fine. If I elaborate it as E plus E exactly, then here E again I can elaborate it as E plus E exactly. Then E value will be what? One more E value we have is ID exactly. So ID plus ID plus ID. So this is what one parse tree what we can generate for this particular string. Then the second possibility is what? Like E derives E plus E, same. Okay. Later, the left side. Okay. Sorry, here I forgot to tell one thing. Okay. We are using the same kind of a recursion. Left recursion. Here also we are using the left recursion over there. Means the leftmost non-terminal should be processor first, then we need to go for the right. Okay, so here we have only one like non-terminal, so we don't have a left recursion and right recursion possibility over here. Then elaborate it, E plus E we have. Then the left recursion we are following over here. Then the leftmost non-terminal should be processor first. Then we are placing E as ID exactly. Fine. Then later plus. Then E will be elaborated as E plus E. Then again leftmost we are following. E will be like derived as ID. Then later the right E will be derived as ID exactly. So here ID plus ID plus ID you are going to get. Okay. So here see here for this like a particular string using this particular production we are getting two different parse trees over there. Yes, ambiguity exists over here. Then when it comes for ID plus ID into ID, okay, using the same production, E will be derived as E plus E, then E will be derived as ID, okay, then E can be derived as E into E exactly. See, ID we have over here, plus we have over here, what I left with, ID into ID we need to get. For that, the second value of this production we are using E into E exactly. Then elaborate E as ID, E as ID exactly. So ID plus ID into ID you are going to get. The second possibility is what? E will be derived as E into E. Okay. Then the leftmost if I consider, okay, after processing that, E plus E we can place because we need to get ID plus ID exactly. Okay. Later into ID we want. Okay. Into we have E we have over here. Okay. Let it be. No issue. Then first we'll deal with E. Okay. ID. Second E, ID. ID plus ID into E we are having. Substitute E as ID. Then you are going to get ID plus ID into ID exactly. Now, here also we got two different parse trees. Yes, ambiguity exists exactly. Okay. Now, like what is the disadvantage of this kind of multiple number of parse trees exactly? Like for constructing the compiler, fine, for while constructing the compiler, okay, if this kind of ambiguity exists, then your like compiler will be in a loop, like whether it should go for the first one or whether it should go for the second one. So what we need to do, we need to eliminate the ambiguity over there. Okay, now before we eliminate the ambiguity, we need to select which one is a true one. Okay, which one means true kind of parse tree exactly. See here, we are following the left recursion over here. Here also we are following the left recursion over here. Okay, so first like leftmost we need to consider. Okay, the result, see here we are having like four operators over here, plus, minus, multiplication and division exactly. Left recursion means it should move towards the left itself. Okay, so the least level or the last level whatever we are having, that should be in the left position over there. So ID plus ID, it is in the last one, okay, compared to this particular ID. Okay, so here we are having, okay, left recursion, but here just observe the last level is in the right side over there, so we are not considering this as the valid parse tree exactly. So this should be considered as a valid parse tree when we are having all signs plus exactly. Now when it comes for multiplication, see here ID plus ID into ID we are having, right? Okay, so again multiplication is also coming under the left recursion. Okay, so left side itself we need to consider, but observe it carefully. Okay, compared to the addition, multiplication will be having highest precedence. Okay, whenever we get a multiplication should be processed first, later we need to go for the multiplication over there. Okay, so here we got the two different parse trees over here. Out of this we need to check, okay, who is having a highest level. See here multiplication is having highest level compared to the addition. Okay, but here addition is having highest precedence, okay, compared to the multiplication over there. So this one is wrong exactly. Okay, if you have a result like, or if you have an expression like 3 plus 5 into 5, okay, so what should be the result? 5 into 5, 25 plus 3 exactly, which will be equal to 28. Okay, so if you are following this, we are solving the multiplication first, then we are going for the addition. Yes, this is true exactly. But if you are following this, addition should be performed first. Means 3 plus 5 into 5 equal to what? 3 plus 5, okay, into 5 exactly. Fine, 3 plus 5 into 5 exactly. We are going to get a wrong result over here. Okay, instead of this 28, we are going to get a wrong result over here. Okay, so the second parse tree is wrong, the first one is the right one. Okay, now how we can restrict the production that it should not generate the second version of this particular parse tree exactly. See, based on the rules of associativity, if you are using a plus minus multiplication division, then the parse tree should grow towards the left hand side itself. It should not go for the right side. So based on that, what we can do, we can restrict the growth of parse tree to left, then we can avoid right recursion over there. How we can do this? See here, this production whatever we are having, so here we have a possibility, like multiple possibilities of getting a parse tree over there. This should be avoided. Now the same production we are using for this particular string. So eliminate ambiguity for string id plus id into id and id plus id into id exactly. So all are plus 1 plus 1 multiplication we are. How we can do this? We can alter this particular, just observe, we can alter this particular production into this form exactly. What is that? E derives e plus id or id exactly. Means here we are following a left recursion. What is left recursion? See here, left hand side of the production is same in the first character of the right hand side over there of the production. This consists of left recursion possibility over here. See, in case of this e plus id, what is the another value of e exactly? Id exactly. Means we can get id plus id when we substitute this particular. Can you get any other parse tree? No. See here, e value we have. What is the value of e? Either id or e plus id exactly. Now I substitute e plus id exactly. Fine, let it be. Then what is the version you want to get? Id plus id plus id. So plus id, last one we already have. First two id we need to get. For that, e will be elaborated as id plus id we need to write. Like this e value we are elaborating it as what? E plus id exactly. So e plus id. So at last e will be elaborated as id exactly. So left recursion we are following. So we are getting only one parse tree. Other than this, we cannot generate any other parse tree for this particular production. Clear? Then next, see here, id plus id into id we are having, right? For this we are going to alter this particular production as this way. What it is? See here, e derives e plus t, or else t, then t derives t into f, or f exactly, f derives id exactly. See, we are trying to avoid like multiple possibilities of generating the parse tree over there. Fine. Just observe it carefully. If I write e, elaborated version as e plus t. Fine. See here, e plus t. Fine. Then what is the value of e? See here, e value can be t exactly, right? Then t value. Let it be. Left recursion only we are following. We'll solve the left one. T. Yes, it is a terminal. Then in the next level, what we do? We substitute t value as f, because t is having a value called as f also. So f it is. Then what is the value of f? Id exactly. Then after processing the left side of this particular like parse tree, we are going for the right side. What is that? T exactly. What do you mean by t? T into f exactly. T into f exactly. Now what does t stand for? T stand for f. What does f stand for? F stand for id exactly. Then later come back to the f. What does f stand for? Id exactly. So this will be processed first. Later we are going to process this particular id exactly. That means multiplication we are providing the highest precedence compared to the addition over here. Fine. This is how we can eliminate the ambiguity over there. If you have still doubt, you can go through some YouTube videos. There like it will be explained with any other examples over there. If you have any doubt, or if you want to solve more examples on the elimination of the ambiguity, you can go through the YouTube. You can find different examples. So these are the like standard example, like id plus id plus id, then id plus id into id exactly. What we need to do, the original production what we have, this should be altered so that you should not get a multiple parse tree. That's it. You should not get a multiple parse tree, and you should follow the left recursion. Remember one thing, you should follow the left recursion. Why we are restricting for the left recursion? Plus and multiplication both are left associative. Both are left associative and left recursive. Remember this. Because of that, we are following this kind. Next subtopic, elimination of left recursion. I told you, right? Left recursion means left hand side what norm terminal you are having. In the right hand side of the production, the first value will be the same. Right hand side of the production is equal to the first character in the left hand side over there. So same. That will be considered as left recursion kind of a production. Left recursion we have the first symbol on the right hand side of the production is same as the symbol on the left hand side of the production. Example we have general form, a derives a alpha or beta you are having. Okay, so this is what one of the general form of left recursion over here. Okay, so in the right hand side and the left hand side, both side you are having capital A. Just observe. Okay, if you are considering this particular production, okay, just observe here. So what you have, A derives A alpha or else beta. So this, if you are considering it as a production, left hand side what you have, non-terminal capital A, and what you have in the right hand side as a first character capital A you are having, both are equal. Okay, then we consider it as left recursion. Okay, fine. So this is what the general form, and this is what the example. Okay, E derives E plus T or T. So this there is in the first the production also we have a left recursion kind, and the second also A derives A small a or else small b. Here also we have a left recursion over here. Okay. Then when it comes for right recursion, you may ask what exactly right recursion is. The rightmost symbol on the right side of the production is same as the symbol on the left hand side of the production over there. Okay, so here we got a general example, just you can have a difference. Okay, A derives A alpha you had in the left recursion, but here you are having A derives alpha A. Okay, means in the right hand side, okay, in the right hand side you won't be having a first letter as a equal non-terminal over there. Okay, you'll be having the next one, right corner of the production. Fine, you will be having the same non-terminal what you have in the left side. Okay, so these are the few examples of right recursion and all. There are two types of left recursion. Okay, we call it as immediate left recursion and indirect left recursion exactly. Okay, immediate means it will be followed like immediately exactly. A grammar G is said to have immediate left recursion. Okay, if it has a production of the form, okay, A derives A alpha. Example, see here we got three different examples over here. E derives E plus T or T exactly, then T derives T into F or F derives open bracket E or ID exactly. Okay, so in this grammar first two productions are immediate left recursions exactly, third one is not. Okay, because left hand side you are having capital F and in the right hand side you are having a open bracket. Observe it carefully, open bracket you are having, both are different, so it is not a immediate left recursion it is. Okay, indirect left recursion we are having. Okay, we'll see that what is this indirect left recursion. Okay, a left recursion involving derivation of two or more steps, so that the first symbol on the right hand side of the particular right hand side of a partial derivation is same as the symbol from which the derivation start is called indirect left recursion over here. See, like after going going through like 2 or 3 steps of derivation, if you are generating, okay, like the left hand side and the right hand side equal, okay, then we are considering it as indirect. See here, E derives what T derives what F, okay, and the third production what you have, F derives E plus T you are having. Okay, can I get F in the place of E in the third production, F in the place of F in the place of S? Okay, can we get? Yes, it is possible. Okay, how it is possible? Not in the third production, in the first production, sorry. Okay, first production is what? E derives T derives F, and F derives E plus T or ID exactly. Now, if I place T as F in the first production, what you are going to get? E derives F you are going to, E derives T you are going to get, right? See, don't get confused. Okay, E derives T derives F derives E plus T or ID you are having. Okay, so now we need to go for some derivation, okay, to bring this production in the format of a indirect left recursion over there. How we can? See, the first production E derives T, what you have in the place of T. Okay, if I place the second production, okay, what it is? T means F exactly, right? Okay, so directly I can write like E derives F. Then what exactly F stand for? F derives E plus T or ID exactly. So if I replace F in the first production by E plus T or ID, then what you are going to get? E derives E plus T or ID exactly. So again you are going to get the indirect production itself, or else indirect left recursion production itself. Okay, so this variety we consider it to what? Indirect left recursions exactly. Okay, now we'll go through what are the problem we may face, why we need to go for eliminating this like left recursion, we'll see that. Okay, problems in left recursion grammar. Okay, a grammar is left recursive, okay, if it has a non-terminal a, such that there is a derivation a derives a alpha for some string alpha exactly. Okay, same thing what we had discussed already. Okay, like if there is a possibilities of left recursion, okay, that condition they are going to explain, okay, later. Top-down parser methods cannot handle left recursion grammar because there may be chances of entering into infinite loop over there. So a transformation is needed to eliminate left recursions over there. So in case of bottom-up parser, we don't have any issue, but in case of top-down parser, the next one, okay, we are discussing about the parser itself, right? Okay, so like in the next topic, we are going to discuss what exactly top-down parser is, what exactly bottom-up parser is. Now, in case of top-down parser, if you are having a left recursion property, okay, then it will be entering for an infinite loop over there. So what we need to do, we need to eliminate this left recursion property over there. How we can eliminate this? Okay, we'll see that. Very simple. Okay, general form of left recursion grammar is a derives a alpha or beta. Okay, it can be converted to a non-left recursion grammar using production as shown below. Okay, so we need to convert this a derives a alpha or beta, what we have the general version, into the format. What it is? A derives beta a1. Okay, or a dash we call it as. What does a dash stand for? Alpha a dash or epsilon exactly. See, what all this string we can generate from a derives a alpha or beta, same thing can be generated from these two productions exactly. Clear? Okay, see, in case of a derives a alpha or beta, okay, which is the general form, okay, there are two possibilities over here, right? One is what? We can get a alpha. Okay, second is what? Beta we can get, or option we are having. Okay, okay, first we'll deal with this beta. Okay, then a alpha will vanish, right? Okay, we won't get. Now just observe here, we got a two production. How to get only beta? What is the first production? A derives beta a dash. Okay, if I substitute a dash as epsilon, because the second possible value of a dash is what? Epsilon exactly. What you will be left with? Beta exactly. Means from the first production easily I can get beta, single value. Okay, now fine. If I want to apply a derives a alpha continuous, okay, then what will be the possible output you are going to get? A alpha first time, then a alpha alpha you get, then a alpha alpha you get, a alpha alpha you get. Okay, like that it continues exactly, right? Okay, now we'll see that same output whether we can generate from this. Okay, we'll see that. Okay, and at last, see here, at last, what is the like a alpha 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 only you are going to get. What is the value of a? If I want to convert the non-terminal into a terminal, then finally I need to substitute beta over there. Then what will be the final string? After any number of time applying the a derives a alpha or beta, you will be getting a string. Observe it carefully. Beta followed by number of alpha exactly, right? Same thing we can generate over here. See here. Okay, in the first production a derives beta a dash you are having, right? Forget about beta. Substitute a dash as alpha a dash. Substitute a dash as alpha a dash. Then what you get? Beta alpha a dash you get. Second time beta alpha alpha a dash you are going to get. How many times if you want to apply, you can apply over there. Okay, later a dash should be substituted as epsilon exactly. Okay, then what you will be left with? You'll be left with beta followed by n number of n number of alpha exactly. Clear? Okay, we are not going to change the meaning of this string, or we are not going to change the output of this string. Only thing is what? This left recursion. See here. Okay, what you have? A you are having. What is the first value of the production over here? Beta you are having. You don't have a I. So we eliminated the left recursion property. Then a dash you are having. What you have in the next? Alpha you are having. Then left recursion property vanish exactly. Okay, so here we got some algorithm over here. Okay, arrange non-terminal in order like a1 comma a2 comma till an for each value of I from I to n. Okay, for each value of j from 1 to I minus 1. Okay, replace ai aj gamma, okay, by production. So this is what the version of left recursion exactly. See here, ai, okay, aj, fine, gamma. Okay, if these two are equal, okay, then this should be replaced by a production of what variety? See here, ai delta 1 gamma, delta 2 gamma, like this we need to. Okay, see how we did over here, same thing we are going to perform. Okay, then at last in case of aj, whatever we are having, aj what value we are having, right? Okay, so that should be considered as delta 1, delta 2, delta 3, like that. Okay, then eliminate the immediate left recursion among ai production. Okay, what is that ai production? Ai production, exactly. Okay, so this is what the small algorithm we have. Okay, and here we got some examples of eliminating the left recursion over there. See, first example, we have e derives e plus t or t derives t into f or f derives open bracket e close bracket or id we have. Okay, so in the first two productions we have a left recursions over here. Okay, how we can eliminate this? See here, first before going for eliminating the left recursion, just observe what is the possible string we can generate from the first production. See, e plus t, what is the possible value of e? Will be t, exactly, means t plus t you can generate, right? Okay, t plus t, again plus t, again plus t, like that we can generate. So instead of that, what we can do, e will be made as t e dash. See here, e will be made as t e dash, exactly. Okay, then e dash should be what? Plus t e dash, exactly. Okay, plus t e dash, exactly. Means when you are elaborating, you will be getting like t plus t plus t plus t plus. Okay, using that left recursion production, exactly. Same thing it should be generated. Okay, at last for e dash there should be a value called as epsilon. Okay, then see here, initially you have t. Okay, see here, initially you have t followed by e dash. What is e dash? Plus t e dash, exactly. So what will be the output if I substitute e dash as epsilon? Okay, t plus t you are going to get. What you can generate from this? Same, right? Okay, like that. Okay, second one, see here, t into f or f we are having. Okay, what will be the final outcome? Like f into f we can generate. Okay, right? So here t derives f into t dash, exactly. What is this t dash? T dash will be star f, exactly. What will be the outcome if I substitute t dash as star f t dash? Okay, we are going to get f into f followed by t dash, exactly. T dash later you can substitute as epsilon over there. So here in the last production we don't have a left recursion over here, so it will be as usual. Okay, so here you got some examples. Okay, please go through this. Then the last topic of this writing, the context free grammar. Okay, left factoring we call it as. Okay, a grammar in which two or more productions from a non-terminal a do not have a common prefix of symbols on the right hand side of the a production is called left factored grammar, exactly. Okay, so now we'll see this, what exactly the general form of non-left factored grammar, exactly. A derives alpha beta 1 then alpha beta 2, exactly. So this is what non-left factoring grammar, exactly. Okay, okay, equivalent left factoring grammar means what exactly? Okay, we'll see that left factoring grammar. Okay, so here we have a derives alpha a1. Okay, and a1 means what? B1 and B2. Okay, left factoring grammar. Okay, so here we don't have a left factoring grammar. Okay, here we have. Okay, so now we'll see how we can deal with this left factoring grammar over here. So here we got one example. S derives AB A or AB B, exactly. So here just observe there are two different like possible values of S, exactly, but they are having a common prefix. Okay, so this indicates what? Yes, it is left recursive. Okay, so here that left factoring, okay, we were discussing about left factoring. Okay, so this is what, see here we got a two different gesture. Okay, one is what non-left factoring grammar and one is what the left factoring grammar. What we are expecting is left factoring grammar only we are expecting. Okay, see in case of non-left factoring grammar there are two possible values of a which is having a common prefix over there, alpha and alpha. Okay, beta 1 and beta 2 are different. Okay, so this we consider as what? Non-left factoring grammar, exactly. Okay, this version we are not expecting. Okay, what we are expecting? We are expecting left factoring grammar, exactly. What it is? See, same thing if you are changing, okay, the prefix, that's it. Prefix should be changed anyhow. How it can be? See, what is the production we are using? A derives alpha beta 1, okay, or else alpha beta 2 we are using. But here we are changing it as what? A derives alpha A1, that's it. Two possible values when we have, okay, there we can check the prefix, make it as 1. Okay, make it as only one possible value for capital A. Okay, so here we had a, in case of non-left factoring grammar, we had a two different possible values for A, that is converted to a one possible value over here. Okay, just observe, A derives alpha A dash exactly. What does A dash stand for? Beta 1 or beta 2 exactly. What are the possible value we can generate from this production? Alpha beta 1 or alpha beta 2 exactly. What is the possible values we can generate from this particular two production? Same thing, alpha A dash, sometime I can substitute it as beta 1 or else beta 2 exactly. What will be the final outcome? Alpha beta 1 or alpha beta 2 exactly. So if any grammar, if it is not in a format of if it is in a format if it is not in a format of left factoring grammar, okay, just bring it in a format of left factoring grammar over there. Okay, so now here we got a non-left factoring grammar example. S derives AB A or AB B exactly. So here AB we have as a common prefix for two possible values of production S exactly. So this can be eliminated. How we can eliminate, we'll see that. So S will be derived as AB S dash. What does S dash stand for? A or B exactly. Okay, so whenever the possible values we can generate from S is what? AB capital A. What is that capital A stand for? Double A exactly. Okay, means AB AA we can generate, or else second possible value AB A B again. Okay, see here B value. What is that? AB we have. Okay, what is the value of capital A? Double A exactly. So if I get if I substitute capital A as double A, the possible output is what? AB double A we get. If I substitute capital B as AB, you are going to get AB as the output over here. Okay, now we'll see whether the same output we can generate from this. Okay, S derives AB S dash, then S dash derives A or B exactly. Okay, fine. Now first I substitute A as S dash as A. Okay, then what you will be getting? A B small letter, then capital A you are going to get. Capital A, if I substitute it as AA, what will be the output? AB double A you are going to get. Okay, same thing what you are going to get from this kind of production. Okay, sorry. Okay, then in case of B, okay, if I substitute S dash as B, okay, then A B capital B you are going to get. Then B, if I substitute it as AB, then the outcome will be AB exactly. Okay, so here we have some algorithm. Fine. So if we are having such kind of prefixes, okay, that will be eliminated from this algorithm exactly. Very simple. Okay, for each non-terminal A, find the largest prefix alpha, okay, common to two or more alternatives. Okay, so here that common alternative existing example we have A derives alpha beta 1, then or else alpha beta 2, or else okay dot alpha beta n, and finally we have a gamma. Okay, another possible values of A exactly. Okay, we'll see that. Then we can write this as what? A derives A derives alpha A dash or gamma exactly. Then A dash will be either beta 1 or beta 2 or till beta n exactly. So same thing what we can generate the output from this particular non-left factoring grammar. Okay, same thing we can generate from these two also. Okay, so this is what we call it as left. What was the topic? Left factoring grammar exactly. Fine. So in the next class we'll discuss like top down parser and bottom up parser. Fine.